Hey everyone, welcome back to The Explainer. Today, we are diving into something absolutely wild. It's a breakthrough AI robotics concept called domain arithmetic, or DART for short. Have you ever wondered why a highly advanced multi-million-dollar robot can flawlessly master a chore in a pristine lab, but then completely faceplants when you put it in your kitchen? Well, we are going to explore how researchers are using a really clever word math trick to fix one of the biggest bottlenecks in modern robotics.
Okay, imagine two almost identical kitchen setups. We've got a robotic arm, a mug on the counter, maybe a microwave. The only difference? The camera angle is shifted just a tiny, tiny bit. For you and me, that is literally nothing. You'd still grab your coffee without a second thought, right? But for the massive vision, language, action models running these robots, that tiny shift is absolutely catastrophic. I mean, game over. And this brings us to a huge real-world headache. Why exactly does moving a camera just a few inches, or even just changing the lighting in the room, completely shatter a highly trained robot's ability to do its job? We call this an environmental shift, and honestly, it makes the success rates of these state-of-the-art machines just completely plummet. So, to really appreciate the sheer genius of today's solution, we kind of need to look at why our current fixes are, well, failing pretty miserably. When a robot completely forgets how to work just because a camera moved, engineers have to step in. And reteaching that robot is insanely expensive, it takes forever, and it is a massive roadblock to actually getting these helpful machines out of the lab and into our homes. Traditionally, scientists have been stuck between two really bad choices. On one hand, you have full data fine-tuning. That means spending months reteaching the robot everything from scratch, which costs an absolute fortune. On the other hand, there's a shortcut called one-shot fine-tuning. You just show the robot one single demonstration. It's fast, sure, but it basically gives the robot complete amnesia. It masters that one specific trick for the new room, but literally forgets everything else it used to know. You can actually see this exact one-shot failure play out in the data. The robot learns the new, adapted task perfectly fine, but if you look at its held-out tasks, meaning all the other chores it already knew how to do, its success rate completely tanks. It adapts to the new room, but forgets its other jobs. It's exactly like learning how to cook in a brand new kitchen, but somehow instantly forgetting how to boil water. It just doesn't scale. But what if we could fix a robot's physical brain using a trick from language? You might actually know this famous AI word math analogy. You take the mathematical concept of queen, subtract king, add man, and boom, the AI outputs woman. Well, researchers had a pretty wild thought. Could we take this exact same math and apply it to a robot's physical chores? To pull this off, we have to talk about the update vector. Don't worry, it's simpler than it sounds. It is literally just the mathematical footprint of what changed inside the robot's neural network when it learned a new skill. It is the exact mathematical difference between the untrained baseline model and the newly fine-tuned one. And when researchers started digging into these update vectors, they made a really stunning discovery. A robot's learning is actually made of two separate Lego-like mathematical pieces. And the crazy part is they don't interfere with each other. One piece is the task knowledge, like how to physically grab a cup. The other is the environment knowledge, like understanding the camera angle or the layout of the room. When you map this out, a beautiful hidden structure actually appears. Different environmental shifts, whether it's a slightly new viewpoint, some camera noise, or different lighting, they aren't just random chaotic errors. They follow highly structured, predictable mathematical directions in the robot's brain. Similar changes in the room produce similar math. The robot is basically building its own natural geometry of the space. So, knowing that the task and the environment are just separate mathematical building blocks, researchers created DART, domain arithmetic. And this is a real game changer. DART lets a robot adapt to a completely new environment across all of its known tasks just by watching one single demonstration. The process itself is elegantly simple. Step 1, compute the update vector for the new environment based on that one quick demo. Step 2, mathematically subtract the update vector of that exact same task from the old environment. Step 3, once the task knowledge perfectly cancels out, you are left with pure, reusable math that represents the new room itself. By extracting this pure domain vector, we can do something that feels like science fiction. If the robot sees a shifted stovetop, we just extract the math of that new angle and essentially copy-paste it onto every single other chore the robot knows how to do. We just plug that domain vector back into the base model. It is exactly like walking into a strange, dark room and finally getting your bearings. Now, of course, there's a catch.
Direct mathematical subtraction inside a massive neural network is rarely perfect. The fine-tuning process inevitably introduces random artifacts. So a direct subtraction often amplifies messy, completely irrelevant noise. And that noise can severely confuse the machine, ruining that pure domain vector we just worked so hard to isolate.
To fix this, Dart uses an incredibly clever method called subspace filtering to map out the robot's neural geometry. Rather than blindly taking a sledgehammer and subtracting the old task from the new one, the system acts more like a scalpel. It analyzes the specific components in the weight vectors to guarantee they actually align before making any cuts.
You can think of subspace filtering as a high-tech pair of noise-canceling headphones, but for robot data, it looks closely at the geometry of both the old and new tasks. If the underlying math aligns, it knows those are shared features and safely subtracts them. But if they don't align, it just filters them right out, totally muting any random artifacts from the source data.
And it pairs this with subspace scaling, which acts as a brilliant built-in safety mechanism. It dynamically checks the alignment between the old and new environments. If it detects that they are fundamentally mismatched, it just turns down the volume knob on the domain vector, preventing extreme noise from corrupting the robot's brain.
So when you bring together that simple word math analogy with this advanced subspace noise filtering, you literally hit the holy grail of robotics. Instead of relying on expensive full data tuning or that failure-prone one-shot tuning, Dart gives us incredibly efficient adaptation. It cleanly transfers only the knowledge of the environment, saving a massive amount of time in data processing. And the benchmark data absolutely proves it. Whether the camera view shifts just a tiny bit, a moderate amount, or totally moves to the other side of the room, Dart vastly outperforms all those older, data-heavy fine-tuning methods. It maintains a super high success rate across the board, and it does it without needing massive new datasets to chew on. The real takeaway here is that a robot arm can now seamlessly switch between totally different tablet tops and vantage points. It completely removes the need for a huge team of engineers to babysit and retrain it for weeks. It just watches one action, one single time, and instantly grasps the geometry of the new space. By treating physical AI adaptation like simple word math, just subtracting the task to isolate the room, we are unlocking robotic systems that are highly scalable and deeply adaptable. We are talking about machines that don't just survive in pristine, perfectly static laboratories, but can actually handle the chaotic, unpredictable nature of the real world. Which leaves us with one incredibly exciting question to think about. As this technology continues to scale up, what happens when a robot only needs to be shown how to clean up exactly once in your specific home, and then it just masters it forever? The era of a truly adaptable household robot is coming fast, all thanks to some clever domain arithmetic. Thanks for tuning into this explainer, and stay curious.